Okay, let's go and take a look at a quick review for related rate problems. And again, I know they become difficult because there's a million types of related rate problems we can encounter. So you want to make sure you go through the examples in our textbook in addition to the homework problems. And again, don't forget you have access to, not that, you have access to the homework help, right? That you have at each of the modules, right? So don't forget you have access to that as you go through that. And then you want to practice those. You want to go over and try other ones, look for other problems. It's just a lot of practice and looking at different types of setups for it. Where is my homework help? There it is. So just to remind you again, you have the homework help that you could look at and kind of the hints and solutions I've kind of hopefully kind of guided you through as you go through them and look at some more of these examples here. So again, I want to emphasize again, as you look at some of my support here, remember the problem solving strategy for related rate problems. And again, it's not as easy as this says, but this is the steps you will take to be successful in that. So take your time, go through the examples here, the extra examples. You can either do a checkpoint so that you can look at the answers later down below, the answers to the checkpoints, right? But again, that strategy is what we're going to use. So I'm going to do two problems that are not here so that you have extra problems to look at. So let me share my screen real quick. Over here, I think you got it here. So let's go ahead and just take a look. It's already solved for us, but let's talk through some of these problems here. So two people are on an elevator. At the same time, one person walks away from the elevator. So you get off, one's going to walk away. The other is going to start going up, and each has some rate of change, their speed. And so what's important about a related rate problem, we're going to start studying the relationship between the variables, the rates of change of those variables, right? How does one influence the other? How does one react to another with respect to another variable potentially, like in this case, the distance between two objects as they're moving. So it really does sound pretty complex at the beginning. And once you get the hang of it, these actually become kind of fun, I think, but let's go and take a look at this. So at what rate is the distance between the two people changing 15 seconds later? So that's the time component. Go back to what we want to do. You always want to set up thinking about the steps we take. Right? We want to assign symbols to all variables involved, draw a figure if possible. So it ends up being a triangle approximately where someone's going up and walking away. And you have variables to represent those distances, right? And then the rates of change, those distances are changing. So we want to determine Z prime as the heading is in this case here. We want to determine Z prime. Here, if we label this X, Y, Z, we're looking for Z prime, right? The rate of change for Z, dZ, dt, or Z prime. So again, whatever notation we're looking for dZ, dt, right? What does that equal at time equals 15 seconds? And that's what we're trying to solve. Now, after 15 seconds, we know something. At 15 seconds, we know X prime and Y prime, which again, we know dx dt equals 2, and then we know dy dt equals 7 given conditions here. So we now know the rate of change, and now that is going to be changing with respect to as this is going up and this person's moving. So now we have to think about what relationships, now that we've stated the variables, right, and the given information that we have. We want to find an equation relating them. And so many times this involves the geometry because related rate problems are with respect to things that happen in the world. And so in this case here, Pythagorean theorem would work. And then we need to turn that equation into a differential equation. And you do that using implicit differentiation. So you can see everything is with respect to time, right? It's d this, dt, and derivative of this, right, with respect to t. It's on the wrong side, but we're taking the derivative. And then we're looking for Z prime or dZ dt. And so then this is the equation we're looking for. So now notice it looks pretty complex, but we have values because we're trying to solve this at time equals 15. So to finish this problem off, right, we use the chain rule to use implicit differentiation, both sides, and then you isolate, right? You isolate that variable we're trying to solve for, and then we're going to go ahead and substitute known values. And so to finish this problem off, you can see in this case, I know the distance at 15. So this is where students get a little confused, is because they have to apply, I have to calculate that distance. X is equal to 2 times 15, or 30 feet. And then the Y is 105 feet. And once you have that at 15 seconds, I can then calculate Z, that distance. And now that you have all of those values, you then substitute into this here. So it seems pretty easy when I do it, I think. But again, there's a process and mechanism, right, of we go about how solving these problems. And this is just another example. And now we relate all these variables and then the rates of change. Let's look at one more here. Let me see if I can zoom in. You can always pause and look at the solution if you need to. So we have here a thin sheet of ice, right? Forms a circle if the ice is melting. So starts to think about that. Melts away such the area of the sheet is decreasing at a rate of 0.5 meters per second. At what rate is the radius decreasing? So we have these variables as you start to think about it. We know, again, think about all the variables and symbols and figure that we would need. And so I can see that we have the sheet of ice, we have a radius, right, within there. And then we know the area is pi r squared, as it has here. And so we think about it, if this area is getting smaller, right, the radius is getting smaller as the area starts to decrease. You can imagine that going on. So what we're looking at is at what rate is the radius decreasing? So we're looking for r prime, or dr dt. What does that equal? We want to know, when does that equal? When the area equals 12 square meters, right? Meters squared. So we have some variables. We now are going to then take the derivative of this so that we can incorporate the rates of change. We're looking for dr dt. We know that the area dA dt equals 0.5, right? It's rate of change. And notice that it's in a different units, because this is technically your acceleration. And so that we have here, once we know those values, we take the derivative, the chain rule, right? You're doing the derivative of the area, everything with respect to time, right? Related rates within time. And so once you have that, you end up with a prime equals 2 pi r prime. And then I think we have all the values. We have 12. We're looking for r prime in this case. We have to solve for r when area is 12, and you can see we get that. And then you can, if we wanted to solve for r prime, we could. Here in this example, we didn't, but r prime is equal to a prime over 2 pi r, and we can just substitute. And now you have your rate. And it's negative in this case because the radius, remember, is decreasing. It's getting smaller. So all I can suggest is make sure you know the problem solving strategy. You know how to do that. And then also practice more. Look at some of the samples. Here's 2 more that you can use, hopefully, to help guide you to think about how to solve it.